All right. Hello, everyone. Welcome to my presentation. My name is Nazanin, and I'm a first-year PhD student in Industrial Engineering and Operations Research Program at UIC. Today, I'm delighted to present one of our most recent works to you, which is Fair and Diverse Allocation of Scarce Resources. So here's today's agenda. We will have a brief introduction at the beginning, mainly to motivate our topic. And then we will talk about the problem, fairness, and we will see some of the most recent related works. And then after then, we will get into our fair and diverse allocation model. And we'll also talk about solving the problem using an algorithm. And lastly, we will show some of our implementation results. A little bit of an introduction. Today, as we're talking, COVID-19 is still spreading in the US as well as across the globe. If you look at the CDC website, you can see that the coronavirus is spreading in different regions in the United States. And as of today, more than 200,000 people have lost their lives to the virus. And as a result, many countries and organizations are working hard and are working together to find a vaccine or treatment for this virus. The main motivation behind our work is to address the problem of an effective allocation once these resources become available to us. So we believe that these resources, whether it's a vaccine or a treatment, are going to be scarce or limited at the very beginning, and it's crucial that we have some predefined strategies so that we know how to allocate these resources in order to save lives. Next, I want to talk about COVID-19 specifically because even though the virus is spreading everywhere, it's not affecting all people in a similar manner. For example, if we compare people based on their race, we see that Black or African American people have higher chances of dying due to this disease. And also, if we compare people within different age groups, we can see that as you get older, you have higher chances of hospitalization, and that's due to the virus. So this means that we really need to consider the demographic disparities, and we really need to consider demographic attributes in different regions in order to have an effective allocation model. So we aim to design a fairness-aware vaccine or in general resource allocation framework. In order to do so, we're going to use two guiding principles, which are geographical diversity and social group fairness. In other words, we think that in order to have an equitable resource allocation model, we really need to consider both a total population as well as a population of more vulnerable people. Next, I want to talk about fairness and more specifically fairness in decision-making problems. So fairness in decision-making problems is about establishing some standards in our decision-making so that the results of our decisions will affect everybody in an equitable manner. If you look at the history and also the literature, we see that fairness in decision-making problems was being mentioned in economics and management science at the very beginning, and most recently it gets a lot of attention in computer science and machine learning area as people tend to remove bias from their algorithms and come up with more fair algorithmic solutions. So this table, if you look at this table, I picked it from Fairness in Machine Learning book, and it has all these different notions for fairness. And it's so the notion of fairness that we adopted from the machine learning area, and then we applied the context into our own problem was equal opportunity or equity of opportunity. So this really means that if we want to have an effective allocation model, we need to allocate resources in an equitable manner. So people who lies in different demographic groups needs to have equity in access to these resources. And here I just listed some related works. For example, people were talking about fairness in resource allocation problems back in 90s, but of course the idea of fairness was different. And also, a lot of people were working in the area of more generic problems like medical resource allocation. I also listed some recent works. Just want to briefly compare them to our work. For example, I think most of these three works were considering a coverage problem in which a single resource can cover more than one people. But in our own context, we consider a one-to-one allocation. So in that sense, it's different. And also, they mainly consider a utilization function that they want to maximize. But in our work, we do not consider a specific objective function, and we design our problem as a feasibility problem. And then we will take care of the, trade-off between diversity and fairness. All right, so let's get to our fair and diverse allocation models. This is just like mathematical notation. I'm going to go through some of them really quick. For example, ZJ stands for zip code number associated with center J, and we define sets of all sensitive attributes as I. So this could be race, age, gender, etc. And we formed our demographic group GI by considering different sensitive attributes and their different levels. For example, G1 can stand for Black African American, women, and low income. So we also have E. So E is a binary variable, so it's going to be 1 if the person was being exposed to the virus and 0 otherwise. Also, XJ represents our decision variable, which is the number of vaccines to be allocated to center J. Sij is just the population of group Y in center J, and we also have some parameters. So we define the feasibility problem P1, in which a diversity and fairness needs to satisfy some user-defined thresholds, which we denoted by epsilon D and epsilon F. So these thresholds are going to be set by a decision maker. And the capacity is, of course, limited. So B stands for the total number of vaccines or treatments that are available to us. And so we defined our diversity constraint as dj of x, which stands for each center j. And by this constraint, we're measuring the difference between the expected number of resources allocated per capita in a specific geographical area and over the entire area or city. So we're really measuring the difference between these two. And the way we calculated each of these expected values are just by the fraction of, vaccines to total population. And we also defined our fairness constraint as fi of x, which stands for each demographic group I. So here we are measuring the difference between the expected number of resources allocated per capita if a person was being exposed to the disease and belongs to the demographic group GI with the expected number of resources allocated if the person was being exposed to the disease, the second component. So as you can see, we also put our mathematical derivations here and the way we derive this equation for our fairness constraint. So I'm going to go through them really quick. For example, for the first component, we looked at the different areas. So we put this ZJ in the condition, and it's just conditional expectation, and then we rewrite the conditional probability, and then just computed the probabilities as the fraction of exposed population. And also for the second component, we looked at different demographic groups. So we put GI into the condition, so conditional expectation again. And then we rewrite the conditional probability using Bayes formula. And the way we get these probabilities were based on the fraction of population and also fraction of exposed population. And next, I want to talk about how to solve the feasibility problem P1, because this is going to be difficult to solve. So we actually converted P1 to another problem, P2, and our methodology was inspired by Lagrangian multiplier, in which we put alpha emphasis on fairness component and y minus alpha emphasis on our diversity component. One thing that is really important is that not for every alpha value, P2, the solution to P2 is going to be equivalent to P1. So we really need to tune the feasible range for alpha value in a way that the solution to P2 actually satisfies these user-defined thresholds epsilon D and epsilon F. And that way, by solving P2, we can solve P1. So in our implementation, we actually, relaxed P2 and solve it as an LP relaxation, and then we call that P3. So this is our binary search algorithm and the methodology we propose to tune the range for alpha value. So I think most of us are familiar with binary search. I'm not going to go into the details of the algorithm, but the reason behind our proposed methodology was because we actually proved that our fairness component is monotonically decreasing in alpha, and our diversity component is monotonically increasing in alpha. So we believe that as we divide our regions iteratively and solving the relaxed version of P2, right? As I said, we call that P3, and then evaluate our results, we can actually get into this region in which both diversity and fairness is being satisfied. So both constraints satisfy these user-defined thresholds, epsilon D and epsilon F. So that way, we can actually solve the feasibility problem P1 using P2. Okay, next I'm gonna just briefly talk about some of our implementation results. So as you can see, we use two main data sets in order to evaluate our model. And so the first one was COVID-19 daily cases and deaths. We picked this data from City of Chicago database because they have these positive cases, deaths, and tests, and other information based on demographic attributes like age, race, and gender, which was really nice. And also we picked number of deaths over positive cases and tests in order to evaluate or calculate the exposure rates for different demographic groups, because we think that it can reveal the disparities among different demographic groups in a better manner. So this is the result of our PLS regression. So if you see older people and Black African American people tend to contribute more to the total deaths. So for example, this shows how number of deaths can capture the disparities. And also we use another data set, which is the population data set. We use the Python package called US zip code, and based on the documentation of the package, they are updating their data regularly, and they had demographic information at city and zip code level. So we didn't have the intersectional population that we're looking for in our original model setting, but we decided to apply our model on different sensitive attributes separately. So for example, this is a result for racial groups. So as you can see, we sorted these areas in Chicago City based on total population. And then we compared our fair and diverse model with another model, which we call diversity only. So the diversity only model only has the diversity component, so it doesn't consider fairness at all. And we saw that the allocation result of diversity only was exactly aligned with total population, versus our fair and diverse model tend to do differently. So it was considering both total population and exposed population. So exposed population is just a measure that we defined in order to calculate the population of more vulnerable people that live in these areas. So, and we tuned the alpha value. So we applied our algorithm and tuned the alpha value, and we saw that the results were significantly different. So we believe that our fair diverse model under the tuned alpha value tends to consider exposed population even more compared to total population. And it enables the model to allocate resources in an equitable manner. So this is just the results, a visualization for the results that I just showed. So again, the areas are sorted based on total population. You can see that the diversity-based model is, monotonically decreasing with population, and our fair and diverse model tends to capture some of the disparities, do a little bit better, but our fair and diverse model with tuned alpha value tends to do significantly better. So if you look at these two regions, for example, we can see that the population of more vulnerable people is higher. So we want these regions to receive more resources. And we just repeated our implementation for age and gender group problems, and we saw that our model, performs similarly. So this was just to confirm our results. And that was all. Thank you for your attention. I'll be happy to answer if you answer any questions or hear some comments. Thank you.